The first edition of this textbook, your textbook of Mercer and Sebecki, had this crazy cool example that I am including in your notes, this Hooke's Law example with springs. Okay, so I want to talk about springs a little bit. Suppose you have a spring, it's been cut, and it's just sitting on the ground, okay? Like, I don't care if you're thinking about a little tiny spring or a big spring or even like a shock, right? The shocks on your car, which are huge. And I'm sure there's even bigger ones like on a tractor. But I mean, we can certainly think about springs all over the case. Like we have them built in to hold our batteries in place, yeah? So if they're just sitting there, they are at what we would call their natural or resting length. They just sit there. They're not being pulled, they're not being stretched, and they're not being squeezed and compressed, right? So that's called their natural length. And then let's suppose we attach it to something. Now, this says it's attached to the ceiling of a solid beam. So I think in this instance, they were hanging, right? They were attaching it and then hanging things from it. But this would be like if we put it inside to hold a battery and we would just solder it on, right? And weights have been put on the ends of these springs to use gravity to stretch it, okay? As opposed to compressing it or something of the sort, right? It says, fill in this table based on this picture. Make a graph in the space right here. Okay, so we are given some masses here, and our job is to find out how far did it stretch. Okay, so this dashed line here would be its natural length, and how far did it stretch. Okay, I'm going to zoom in on this image. If you're thinking, where do I find all of this? Your textbook, if you go into Connect Math and you go into your textbook, there is a link to the website of, I forget what university created this. They basically created an app where you could attach however many grams, like change the weight, and it would bounce down. It also shows oscillations because, of course, that is used in other classes like trig and calculus, whatever, DiffyQ. Nonetheless, in this class, it's applicable. I like it. It's so cool. Let's see. This 250 gram, like how far down did this go? Well, this is 5, 10, 15, and not quite to 20. And really that is right in betweeny here. So this is actually a distance of 17.5 centimeters from here to there. Okay, and then when we look at the 100 gram one, while we have it zoomed in at this super zoom, there was 5 and this was 7. Okay, so from here to here was 7 centimeters. And then we look at this little guy. What is that? That's 50, by the way. I know it looks blurry, but this was 50 grams of weight. 50, each gram is a sugar packet, about. So, and this one is, so about 3.5 centimeters displacement or stretch. Yeah? Okay, so I'm going to zoom out. Is that even more clear? That is a little bit more clear even. Anyway, so just so that you see where all of these values come from, how much did it stretch? Let's write that down. So when it was 50 grams, very popular. That was actually another teacher calling me. I'm going to call her as soon as I'm done. 3.5 centimeters. 100 grams stretched at 7 centimeters. 250 grams stretched at 17.5 centimeters. I'm going to fill in some of these gaps. If it had been 0 grams, there would have been 0 stretch. And it looks like for every 50 grams we add, it's stretching 3.5 centimeters. Let's see if that pattern works actually. Oh, please let it work, because I will have to use whiteout if it doesn't. So additional 50 grams and an additional 50 grams. Add on 3.5 centimeters, that would be 10.5. Add on 3.5, that would be 14. Add it. Yes! Yes, the pattern is holding. I see the pattern. For every 50 grams, it is stretching 3.5 centimeters. That is number 2. She wants me to respond. That means she left me a voicemail. Okay. Find the slope. Well, let's see. The slope would be the change in the response. The response is the stretch. So 3.5 centimeters. Okay, the ratio of the change in response to the change in the explanatory variable for every 50 grams of weight. Okay, there's our slope. And say what it means. That could be simplified, but I'm not going to simplify it. Say what it means. It means that the spring, this particular spring, and remember, like, springs differ. Some of them are little tiny and very, very stretchy and springy and bouncy. And some of them are, you know, like hard to even compress, like shocks. The spring stretches 3.5 centimeters for each additional 50 grams of weight. Yeah, got it. Write an equation to represent the values that work in this line. Okay, so I see a pattern for each additional one of the, so this is an increase by 3.5 for each additional 50. But here was our ratio, yes? So let's see, the response. So I'm gonna go back and remember that what does it go? It goes response, that's the distance. What do we want to call this? Distance stretched. We're going to call it D for distance. And we're going to call this M for mass. Okay, here we go. The distance D, distance in centimeters, is equal to, well, here's our rate. So 3.5 centimeters each 50 grams times the mass in grams. So this would be grams and grams and cancel, and this would be 3.5 centimeters, just FYI. Okay, so I just did a quick unit analysis to make sure that the grams and the grams would cancel and we would just be left with centimeters, which is true. So there's our equation, and I just wanted to let you know that really what I was thinking was this. The initial was 0, so there was no initial here, plus how much its constant rate of change is, times how many times that's getting added. Yeah, which is our M. Use your equation to find the mass of each weight shown below. You got it, boss. Let's see what we have here. Oh man, we forgot to graph this. Oh, beans. That's what my kid says. You're like, why does she keep saying that? Oh, beans. And I'm hanging out with her a lot right now. Both of them. I'm hanging out with them a lot right now. Grams is the explanatory. Centimeters is the response, and centimeters of stretch if you want to be real specific. And let's go, we have to go up to I don't know. Maybe we'll just do these first few. Let's go 5, 10, 15, 20. 5, 10, 15, 20. It works. That allows us to get all of them if we like. And we have to go up to 200 or 250. So let's go, I don't know, 50, 100, 150, 200 grams, 250. Okay. Zero, 0 grams, 0 stretch. 50 grams, 3.5 stretch. That is the wrong. That is at 100 grams. Whoops. Oopsie daisies. 50 grams, 3.5 stretch. 100 grams, 7 stretch. 150, 10.5. Got it. 200, 14. 250, 17.5. Okay, I'm seeing it, but it's not, ugh. When I look up here, I'm like, oh man, that's scarily right around 15, but I get it. It's supposed to be a little bit lower, and this one should also be a little bit lower. When I think about 20 coming across here, I'm like, that's a little bit high. Ish. Maybe it's even over here. Okay, whatever. So, straight line. Okay. And know that these aren't perfectly on the line because I was really just eyeballing where they go. I didn't make a grid. My precision of my plotting may be a little bit under question there. Nonetheless, use our equation to find the mass of each one of these. All right. Well, our equation looked like this. And we don't know the mass, but we do know the distance. Okay, so we don't know this red mass, but we do know this is what, 5, 10, 15, 20, 21, 22 about? Okay, so the red one has a stretch of about 22 centimeters, and that's our distance. So we'll go 22 centimeters is equal to 3.5 divided by 50 times the mass. And now I'm going to scale both sides. Up by 50, down by 3.5. Which is exactly what this would do, but make sure there are parentheses if you're going to do this. Right? Okay. What did we just say? So 22 up by 50. Scale it down by 3.5, and we get approximately 314.2857, blah, blah, blah. So the mass is about, let's go 314 grams. Yep, got it. And then the second one, let's see, how far did it stretch? I don't know. About 5, 10, 11, 11 and a half. Okay, let's do it again. Again, we're given the stretch, so we're given the D. The distance of the stretch was 11.5. Okay, we got 3.5. There's our ratio conversion, and 11.5, scale it up by 50, scale it down by 3.5, and we get approximately 164.28571. So our mass is approximately 164 grams. And then the green one, there was a gold one, I love gold. And let's see, that looks like it's about 5. Maybe just over 5, but I'm going to stick with 5. Okay, so this was the gold one, and the green one now, we would follow the same process because we are given the amount, the distance of stretch, and we're finding the mass or the weight. Well, weight and mass in this situation are the same because we're on Earth, gravity, whatever. But let's see. 5, scale it up by 50, scale it down by 3.5. Approximately 71 grams. Okay, so we can use our equation in order to find the weight of each one of these. And I notice that this is direct variation because not only are these proportional, so every 50, so the unit ratio here, for every 50, it's stretched by 3.5 centimeters. So they're proportional to each other. And I also notice that this fits the bill for our y equals mx plus b, where b is 0. Yeah. Is this direct variance situation? Yes. If so, find k. If not, tell why. And I would say yes, 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 because of all the reasons I just said. Yes. So, if so, find k. Here, k equals 3.5 per each 50, which, by the way, how much is that really? 0.07 centimeters per gram. Okay, that's our k value, our constant ratio. If not, tell why. No, this is what's up. And I also want to say that we know that this is a direct variance or directly varying situation because the initial is 0. If you attach 0 grams, then you get a stretch of 0. So that's that. And the next one, we're going to have another example and see if that one is also, maybe it is, maybe it isn't, directly varying quantities.